So simple harmonic oscillations, we saw obey the equation. We wrote it in terms of x, but this could be some other variable. So x is some variable, and the SHO obeys this equation. So we started actually with x equals a cosine omega t plus phi. We can write this in a different form using complex variables, exponential I omega t plus phi, where the real part of this is a cosine omega t plus phi. And in this case, then we have dx dt, or x dot being I omega, a e to the I omega t plus phi, and x double dot, two derivatives in time of x. And if the x is position, then that's an acceleration, minus omega squared a e to the I omega t plus phi. Or we could think of writing this as make this into two terms, or make phi equal to 0. Write this as x equals a e to the alpha t, where we can sort of be a little more general. In this case, we have x dot equals alpha a e to the alpha t, and x double dot alpha squared a e to the alpha t. And so x double dot is equal to minus omega squared x, right? We see that here. And so the alpha squared in this specific case, where it's a complex exponential, is minus omega squared. And so alpha is equal to the square root of this. So it's the complex number I, which is the square root of -1. But this sort of allows us to consider exponentials that are also not complex numbers. So we'll see that when we get to LC circuits. So systems obeying this, we know, the spring, where the spring constant is the mass times the angular frequency squared. The pendulum, we mentioned the pendulum, so let's look at that system. So a pendulum where we attach an object of mass m to a string, say that's the angle theta, and the length is L. If we do a free body diagram, the tension in the string is that way, down this way is mg, and if we want to project this into a coordinate system that has this direction and this direction, which is perpendicular to that direction, right? So orthogonal axes, then we have tension this way, and then we have mg cosine of that angle along this direction, and this way we would have mg sine of theta. So the theta is increasing as we go up, and so when the object has theta equals 90 degrees, we have mg pulling it downwards, and when the object has 0, when it's here, theta is equal to 0. There is no gravitational component here pulling it to the left, of course. So the object is actually moving along an arc like that of length L, and so the distance covered is say arc length S. S is L times the angle. As the angle increases, right, it goes all the way around. S becomes 2 pi times L, because when we go once around, this becomes 2 pi. That's the circumference, as we know. So we can say that a tiny little arc length is L d theta, and therefore we can construct a speed along the arc, which is L times the angular speed, and therefore an acceleration acceleration along the arc, which is related to the angular acceleration. Theta, a double dot, we could call that double dot. And so the ma equals f, right, becomes m times second derivative along the arc here. Ma equals, we're coming down, minus mg sine of theta, and so we have, that becomes, so we'll replace this with this, and so the equation looks like this. Minus mg sine of theta. And so that takes us to two derivatives in the angle. So theta double dot equals, let's bring the L over here. We have minus g over L sine of theta. That's not quite an equation that looks like this for theta, but it can be if we think of small angles, because the sine of angle for small angles is just the angle itself. So as theta becomes small, the differential equation here becomes minus g over L theta, or we can write this as second derivative of theta in time equals minus g over L times theta, and that's just an SHO equation for the angle theta, or let's just write it, right, but it's a different spring constant, if you will, or the analog of the spring constant in this case, right? So it looks like that, and of course the solutions are theta equals, use the same amplitude, A cosine, and by analogy we know that this is omega squared, so g over L square root t plus phi, starting point. We could also write this as theta equals theta naught cosine of g over L t plus phi, in the same way that our solution before could have been x equals x naught cosine omega t plus phi. So we see the SHO equation for a system that is not a spring, and we'll see this for the LC circuit, and then we'll see this for some other system as well, because SHOs are ubiquitous.